if that is your heuristic, which is a really common heuristic for A-star search, do you see that it's not really going to help you that much?
Yeah.
Because even if you're right next to the goal, but there's a wall there, you're not necessarily close to solving the maze. If somehow, though, you could intelligently discern that, and you could tell how close you're getting to the maze, and you could put that into the heuristic, A-star search would really, really rock. It would find its way through the maze without even searching these obscure paths that you don't have to try. Because your heuristic guides it, basically. It tells it, well, come this way. Ooh, come this way now. And, I mean, how hard is it to follow the smell of fresh baked bread? Or
So like
where that came from.
So
Weirdness of my mind.
if you maybe knew like how far each wall forced you to deviate around it, and like how many walls were between you and the thingy,
Yeah.
is that kind of the idea of like how you might improve it?
Yeah, so if you're trying to improve your heuristic, that's exactly what you do, is you start thinking about how can we solve this problem without solving the problem? And you start adding things like, well, if I was down the wrong path because there's a wall here, it'd take me at least 3 to get around it, so we'll just add 3 to our heuristic. And you start putting little logic in there, and the better your heuristic gets, the quicker A-star search can solve the problem, and that's good. But by the time you've solved it really well, you've solved the problem anyway. I personally don't see the advantage of A-star search. It really helps in some situations. Specifically in that case of video games where the user clicks the mouse and you have to take the character there but don't walk through walls, it does a darn nice job. So it's a good algorithm to have for video games and a few other cases. And just because it's not much harder than uniform cost search, you might as well use A-star search and just see what the heuristic gives you, right? Maybe it'll give you benefit, maybe it doesn't. There's no harm in going to A-star search. It's just the slight added complexity of you've got to provide a heuristic. So A-star is a little better than uniform cost. Whoop-de-doo. I'm just teaching you uniform cost because it's slightly simpler, doesn't have a heuristic. Do you feel comfortable with A-star search? Because I can test you on it now and you'll be okay answering questions. By the way, we have a test coming up. Talk about that. I have it on the 23rd. Is that an okay time? I think we'll stick with it. What I will do then is on the 18th, I will basically spend the whole day reviewing for it and answering questions and talking about what's going to be on it, things like that. And so I think you'll feel pretty prepared by the end of the 18th, and then you'll have all weekend to study, then we'll take a midterm, and then we'll just keep on going with the class. Sound okay? Okay. Now, with my remaining 10 minutes, I want to talk about the complexity of high-dimensional space. Okay. Let's suppose we have a problem with only one dimension. Imagine there's only one piece and you can only move it horizontally. So the two possible actions are go right and go left. And we'll say there are 10 discrete spaces, just like on here. How big is our problem space? How many possible states are there? 10. Now we're in two-dimensional space, one piece. You can move anywhere in there. Now how many possible states are there? About 100. Three-dimensional space, 1,000, 10,000, 100,000, million, 10 million, 100 million, billion, trillion, quadrillion, gazillion, Googleplex, whatever. Communicating, words, charades, verbal, explosion, exponential, comprehend. Okay, you know this symbol? This is my favorite sign language symbol because it implies that somehow you're telepathic. The meaning is getting from you to me and going like this. I don't know why that. That's my second favorite sign. I like this one too. what that is. Okay. Okay. That one's cool too. Moving on. My point of this is every dimension you add to your problem adds exponential number of possible states to the state space, right? How much of that state space do you visit while using uniform cost search, usually? Assuming your starting point and your goal are pretty much at opposite ends of your state space.
Pretty much
All of it. What if they're halfway through it? About half, maybe 1 over square root of the number of dimensions. I don't know what. But what if you pick 2 random places in the space? Now how much of your space do you use? I don't know. That's an interesting problem.
Be one of your fancy probability.
I need to go figure that out.
distributions.
But the point is, it's a significant portion, no matter what you do. So if we're doing some type of asymptotic complexity analysis, if we're thinking about, some constant portion of 100 bajillion, that's a big space, right? Even if your goal and your start point and your goal aren't that close together, the amount of region you're going to have to search in this exponentially large space is just crazy large. Let me put it this way. If you were to remove a couple of pieces from this problem, it becomes unsolvable. Isn't that weird? Can you tell me why?
Because there's more options. You mean like
Yeah.
time-wise?
Yeah, that's exactly why.
Yeah.
There's more options. So if I remove a few pieces, the problem gets easier, and that's why computers can no longer solve it. Essentially, the problem gets so easy because there's flexibility. You no longer have to go this direction or that direction. You can go any way you want. And we as humans get a lot more comfortable with that because all of a sudden, instead of being led down, there's only 2 paths to choose from, we can wander any way we want. We kind of use this sort of A-star heuristic-like thing in our head and drift towards the goal, and we believe we get there. In reality, we suck at solving this problem. This is a hard problem for humans to solve. But we have really good heuristics, and that's kind of what makes humans really good at thinking. The computer, though, if you're using uniform cost search, and this piece can move anywhere it wants, and this piece can move anywhere it wants, and this piece can move anywhere it wants, what happens to your frontier? Exponential growth, right? It went from this size to really fast, and pretty soon you run out of memory, and the problem's hard to solve. Because it's a high-dimensional space. People don't really fathom the size of high-dimensional space very well. If I take a cube and I ask how many cubic centimeters are in it, maybe it's 100. If I add another dimension to it, and I keep doing that, very quickly I'm in the billions of 22-dimensional cubic centimeter cubes in this tiny little space. And it just blows people's minds. So there's a quote by Albert Einstein. He was once asked, what is the most powerful force in the universe? This is after he was just instrumental in developing the atomic bomb, which is a powerful force, right? His reply was compound interest. What's compound interest? That's what banks use to rip you off, right? It's or benefit you for putting money in them. It's what credit card companies use to rip you off. What it really is it's exponential growth. And what Einstein was really doing is referring to his nuclear bomb because the energy released from each split of the uranium atoms creates just a little bit more energy in the next split. And so it grows with compound interest, so to speak. But this is a quote that a lot of economists like to use when talking about finance. The point is, exponential growth just boggles human minds. And if you have a problem where you can do more than 3 or 4 things, uniform cost search just falls apart because the state space is too big, and that means it's really hard to solve these problems. Okay, like chess, like Go. If you guys heard that Go has recently been cracked, we finally got computers that can beat humans. That's really cool. We need to talk about that. But I only have 3 minutes and I can't possibly talk about that in 3 minutes. I think we'll just stop here. Thanks for coming today.